actually just lecture 39. Modeling with exponential and log functions. Okay, so we've seen the idea of continuous growth rate when we were talking about money. You can either compound a finite number of times per year, which is the formula that is P times 1 plus R over N to the NT, right? Or we can use the idea of continuous compounding where you compound an infinite number of times over the year. So this idea of continuous compounding can be useful in other contexts as well. You can convert any exponential function that's of the form, the first kind of form we learned about, a times b to the t. You can convert any function that looks like that into a continuous growth function where a times e to the rt. And r is generally called the instantaneous or continuous growth or decay rate. So for exponential growth, r is positive, and for decay, r is negative. Okay, so here's how the conversion from one form to the other works. I want a times b to the t to equal a times e to the rt. I want to figure out values so that these two functions are the same. Okay, so they both have an a in them. I could just divide those out, right? Divide both sides by a. The a is the same value. So I want b to the t to equal e to the rt. Well, e to the rt could be rewritten as e to the r to the t, right? Because when you raise a power to a power, you multiply the exponents. So if b to the t has to equal e to the r to the t, what two things have to be equal? E and e to the r have to be equal. Okay, so from this step to this step, if something to the t equals something different to the t, then my two things have to be equal. So if I know r, I can raise e to it and I get b. And if I know b, I would take the ln of both sides, right? And I would get that r is the ln of b. Because the ln of e to the r is r, that equals the ln of b. So these are my two ways of converting. So r and b are intrinsically related. B is a growth factor, r is a growth rate. Okay, so if you know the growth rate, you can get the growth factor by doing e to the r. And if you know the growth factor and you want the growth rate, you take the ln to get the growth rate. So any exponential function can be expressed two different ways. We're just changing the base from b to e. So here's an example. We've got the cost of bottled water. In 1976, approximately 250 million gallons of bottled water were sold in the United States. And between 1976 and 2000, the bottled water industry had a continuous growth rate of about 12%. Okay, so that's an R value, continuous growth rate. They're talking e to the r, right? And that was actually, that number came up in a report to the New Jersey legislature, a committee on environment. Okay, so we want to construct a model using that number, 12% per year, and we'll use this as our initial value, 250 million gallons. So let's just measure in billions because I don't want to have to write 25 and then 9 zeros. Right? So I'm just going to write 0.25 and say I'm measuring in billions. Okay, so because they gave me a continuous growth rate, my function is going to look like this. A e to the rt, and I'm using a as my initial value. When we talk money, we usually write p there for principal, initial investment. When we talk anything else, we put a for y-intercept, right? It's the same as a times b to the t. All right, so I'm going to put in my initial value, 1/4 billion. E, my growth rate, my continuous growth rate is 0.12 to the t, 0.12 t. So there's my model. This represents sales of bottled water in years since 1976. Sales measured in dollars, nope, sorry, gallons. Sales in gallons of water, and T is years since 1976. So does it make sense where I came up with the equation? If I wanted to write it in A times B to the T form, A would still be 1/4 for 1/4 billion, and B, I would just do e to the 0.12, and that would give me my growth factor. So I could do or y equals 0.25 times e to the 0.12 is 1.127 to the t. So these are two completely equivalent equations. Okay, if I put them both into my graphing calculator, so I'm actually going to take this number. Here's a little trick that you might find handy. I'm going to store that number so that I don't have to write out all the decimal places again. So I'm going to use this button that says STO right above the on button. I want to store my previous answer as the letter A. So I hit alpha A and press enter. Now whenever I type A, it's going to recall this number. So when I go to y equals, in y1, I'm going to put this function, 0.25 e to the 0.12x. And in y2, I'm going to put this function, 0.25 times. And so that I don't round, I'm going to use the number a, 0.25 times a to the x. And I'm going to make the second one bold so you can tell the difference. And let's see, window, this is t is years. So I don't know, 50 years we'll look at. And then y is sales in billions, or gallons of water in billions. So start with 0 because we're starting with 1/4, and then go, I don't know, to 10 billion. And we graph. So there's my first function, and there's my second function. They are exactly the same. So two functions, exactly the same, just two different ways of writing it, of writing the same model. Hey, come on in. Okay, so we've got a model. We have two different models that are equivalent. All right, so we can use those models to answer questions. Beverage Marketing also reported that in 2002, sales of bottled water were nearly 6 billion gallons. So if we extrapolate, what does our model predict for sales in 2002? So I want to plug into this model some value. 2002 corresponds to t equals what? Sure, yeah, I'll get it. No problem. Yes, 26 years. T equals 26. Okay, so let's plug t equals 26 into either of my two models because they are the same. So I'm just going to go to my table, type in 26 years, and I get 5.66 billion. So y of 26, approximately 5.66 billion gallons. So is that good news or bad news that actual sales was higher than predicted sales. I guess it depends on what if they didn't have enough water? This is predicted. This is what our model predicts. Model prediction. Oh, okay. So if you are the bottled water industry and you predicted a demand of this much, you would not have met the demand. Right. So if you are like a CEO of, I don't know, Poland Springs, this might be bad news, right? You might have made a bad prediction. But if you are the Earth, is this good news or bad news? Also bad news, right? Because we're predicting 5.66, which is still a huge growth, right? From a $250 million to over 5 billion in 26 years. But we actually grew more than that. We actually sold more bottles of water than we predicted using the 12% growth rate. But let's see what happens if I predict for 2007. Use my model to predict for 2007. So that would be 5 years later, which is t equals 31. So y of 31, that is 10.3 billion gallons of water. In 2007. So actual sales of bottled water in 2007 were 8.82 billion. So what conclusions can you make now? Good, bad? The model sucks, yeah. Yes, we used fewer than predicted. Yeah. So sold less water than predicted. Okay, so in fact, probably 12% growth rate no longer holds, right? So 12% growth may be slowing down to some smaller percentage. So I suppose that's good news. So when does the model predict that sales will reach 100 billion gallons? So my model is y equals 0.25 e to the 0.12 t. I can use the other version if I want. If you'd rather use the one that looks like a times b to the t, it's the same, so you can use either one. And I want to know how long until I reach 100 billion gallons. So this is the equation I want to solve. Divide both sides by 0.25, and I get 400 equals e to the 0.12 t. Then what? Take the ln of both sides. The ln of 400 equals the ln of e to the 0.12 t, which is 0.12 t. Because the bases will match, you just lift off the exponent. And then divide both sides by 0.12. So that comes out to approximately ln 400 divided by 0.12, 49.92 years. After 1976, which is the year 2025. almost 2026. So we can do a similar thing for radioactive decay. This is the formula we originally had for radioactive decay. Initial amount times 1/2 to the T over H. H is half-life, M0 is initial amount, T is time. We can convert it to M0 e to the negative RT. So it's the same kind of conversion. I want to force M0 e to the negative RT to equal M0 times 1/2 to the T over H. So I got to figure out what things have to be equal to make this conversion. So the M0 is the same in both equations, so I can divide that out. And I get e to the negative RT has to equal 1/2 to the T over H. Now I'm going to do the same little trick I did with the growth one. And I'm going to rewrite e to the negative RT as e to the negative R to the T. And the same little trick over here, I'm going to do 1/2 to the 1 over H to the T. Because when you raise a power to a power, you multiply the exponents. 1 over H times T is T over H. All right, so if I have some stuff to the T equals some other stuff to the T, then the two stuffs have to be equal. So it's got to be that e to the negative R equals 1/2 to the 1 over H. So if I were to solve this equation for R, I would take the ln of both sides, and I would get negative R equals 1/2, equals the ln of 1/2 to the 1 over H. And then I could bring the 1 over H down in front, and I would get R equals negative 1 over H times the ln of 0.5. 1/2. And just to be a little bit fancy, this is the log of a quotient. I can break it into 2 logs. So this would be the ln of 1 minus the ln of 2. And what's the ln of 1? Close. E to what power gives you 1? 0. So the ln of 1 is 0. And if you couldn't think of it in your head, you can just type it in your calculator. So I have negative 1 over H times 0 minus ln 2. Well, 0 minus ln 2 is just negative ln 2. So R is the ln of 2 divided by H. Which means that H is the ln of 2 divided by R. So if you know R, you can get H. If you know H, you can get R. They are related using these equations. Yeah, I know. So in your homework, they might give you a half-life and ask for an exponential decay rate, a continuous decay rate. You would just use this formula, right? If they give you a decay rate and ask for a half-life, just use this formula. So you now have formulas, so you don't have to do this all over again. R is continuous decay rate, and h is half-life. So if you know one, you can always find the other. So in your homework, they might give you one and ask you for the other. And you can just use these formulas rather than re-deriving it. You don't have to do all of this work every time. It says ln of 2. ln of 2. Okay, so we'll do an example and then we'll be done with this for today. Okay, the half-life of radium-226 is 1600 years. Now, don't be confused by the numbers. Very often, radioactive elements are named by like a name and a number. That 226 is part of the name, not anything to do with the problem. So the half-life of radium-226 is 1600 years. If we start with a 22 milligram sample, find a function that models the mass remaining after t years. So I have two equivalent formulas. I could use m of t equals m0 times 1/2 to the t over h. That's the one we've been working with so far. Right? Or I could use this other one that we just showed as equivalent, m0 e to the negative r t. Okay, so since they gave me half-life, I'm tempted to use this one that has half-life in it. Right? Makes sense? So let's do that. Find a function. m0 is 22, 1/2 to the t over the half-life, 1600 years. All right, so there's my function. If I wanted to, I could do the other one. Like maybe the homework asks you to put it in this form or something. They're equivalent. So you can use, yeah. Right, yeah. So if I wanted to use this one, I would have to convert, right? They gave me half-life. I need to know R, right? If I want to use this formula, I would need to figure out what R is. And I would say, okay, well, R is the ln of 2 divided by h, which in this case is 1600. So R would be ln of 2 divided by 1600, the half-life. So I get 0.000433. Approximately. So then I can just plug that in. M of t equals 22 e to the negative 0.000433 t. So those are two functions that are equivalent. They're exactly the same. If you graph them both, they're going to look exactly the same. Two exponential decay functions. So I can use either one when I'm answering the rest of the questions. When will only 2 milligrams of the sample remain? So I'm going to be solving for t. I can in either of these, I'm going to replace the left-hand side of the equation with a 2 and solve for t. I'm tempted to use the one on the right because when I take the ln of both sides, the ln of base e is really easy to do. So if I set 2 equals 22 e to the negative 0.000433 t, divide both sides by 22, and I get 1/11. Sure. Just because you can choose whichever one you want. I chose this one because I thought to myself, I'm going to be solving, which means I'm going to have to take a log of both sides. And I like having base e because then when I take the ln, it'll be easy, right? Because the ln of e to some stuff is just your stuff. But it really doesn't matter. It's not like it's that much harder to do the other one. So now I take the ln of both sides. And the ln of e to my stuff is just the stuff. And divide by this negative 0.000433. So we get t is approximately, I think I'll store this number as a so that I don't have any rounding error. And then I'm going to do the ln of 1/11 divided by a. Oops, a is supposed to be negative, so times -1. 5,535 years. Questions? Okay, so we will start log models next class.